Okay. Hi everyone. Hi everyone. So first of all, let me know, is audio and video everything clear here? First of all, let me know, is audio and video everything clear? Yes. Is audio and video everything clear here? Good afternoon here. Good afternoon all. Okay. Paras Kumar, good afternoon. Basiraj Lokesh, good afternoon here. Anand, hi. Okay. So I hope audio and video everything is clear, right? Okay. So we'll start the subject. So our subject is electromagnetics here. Electromagnetics. So in the previous sessions, we have studied about del operator. We have started with del operator. Yes or no? So we have seen that whenever this del operator operates on scalar function, the resultant operation is gradient. When it operates on vector function, you are going to have two operations, that is divergence and curl. Yes or no? So in that we have started studying about this gradient. Yes or no? So we have seen what do you mean by a gradient and its physical interpretation, how to represent a gradient mathematically. Yes or no? And what is the purpose of gradient? So all those things we have seen in the previous sessions. So then after that, in the last session we have started flux here. Yes or no? We have seen what do you mean by flux. Yes or no? So we have seen that flux is nothing but what here? Flux is nothing but it is a measure of what? It is a measure of how much of the given vector field is penetrating or flowing or passing through a given surface. Yes or no? So I have told that flux is nothing but what? Flux is nothing but it is a measure of, just I am revising here, So whatever we have done in the previous session, so that part I am just revising. Okay. So it is a measure of how much of the given vector field, is penetrating or flowing or passing through the given surface, right? Through the given surface. So flux is nothing but it is a measure of how much of the given vector field is penetrating or flowing or passing through a given surface. So this is called as flux through what? Flux through the given surface. So flux through the given surface. So we can define the flux through the given surface in this manner, right? Okay. So the flux through any given surface is nothing but what? It is a measure of how much of the given vector field is penetrating or flowing or passing through a given surface, right? Okay. And we have seen that this flux is depending upon what here? The flux through any given surface is depending upon what? Is depending upon the magnitude of what? It is depending upon magnitude of vector field. Yes or no? Magnitude of vector field, that is we have considered it as what? F bar, magnitude of F bar, where F bar is nothing but vector field here. Second, it is going to depend upon what? It is going to depend upon magnitude of what? Magnitude of surface area. Yes or no? It is going to depend upon magnitude of surface area, that is magnitude of A bar. So and also it is going to depend upon what? It is going to depend upon the angle between what? The angle between the vector field and the direction of the surface area. The angle between the vector field and the direction of the surface area. So it depends upon angle angle theta between f bar and a bar, right? Okay, so the flux through any given surface is going to depend upon magnitude of the given vector field and the magnitude of surface area, and also it is going to depend upon what? The angle between f bar and a bar. And we have seen that whenever f bar and a bar both are pointing in the same direction, we are getting flux as maximum, and whenever f bar and a bar both are perpendicular to one another, in that case we got what? Flux through that surface will be 0 or minimum. Yes or no? So mathematically, how to represent flux here? How to represent flux? So the flux through any surface in general, we have to represent it as what here? Double integral f bar dot dA bar. So this represents the flux through any given surface. Now here, if f bar is constant, with respect to this integration variables, then you can take this f bar out of the integration. Yes or no? So in that case, you can simply write f bar dot double integral dA bar. This is equal to what? You can simply write f bar dot a bar. So when you can represent the flux in this manner here, directly f bar dot a bar, when you can represent? Whenever f bar is what? F bar is independent of what? Independent of integration variables. Whenever it is independent of integration variables, then you can take it out of the integration, then you can simply represent in this manner, right? Okay, now how to represent the flux through any closed surface here? How to represent the flux through any closed surface? So you can represent the flux through any closed surface in this manner. So closed surface integral f bar dot what? Dot dA bar. So how we got all these representations and everything we have studied in the previous session. Okay, so I hope it is very crystal clear. It is crystal clear about flux. I hope you have understood clearly about flux here, right? Okay, okay. So now see here. Now let us consider. So let us consider this is case 1 here. Let us consider this is case 1. Okay. So this is f bar, and here I am considering a surface. So here I am considering the surface area a bar. So its direction is given by the normal drawn to the surface, So this surface is like this. So if you draw the normal to this surface, it is going to point in this direction, right? Okay. So here, what is the angle between f bar and a bar here? What is the angle between f bar and a bar? A bar, the direction of a bar is pointing in this direction. F bar is also pointing in this direction. So in this case, theta is equal to what? Theta is equal to 0 degrees. And we got here, flux as what here? Flux is maximum. Yes or no? The flux through the given surface is maximum in this case, right? Now if you consider another case here, see here, if you consider another case like this. Now here f bar is pointing, wait. So now here let us say f bar is pointing in this direction here. Let us say the vector field f bar is pointing in this direction. Now the surface area is placed in this manner. So this is a bar. The direction of the surface is given by a unit normal drawn to the surface. Now here the surface area is placed like this. And f bar is parallel to what? F bar is parallel to the plane of the surface. Yes or no? F bar is parallel to the plane of the surface. Now here, what is the angle? Between the vector field and the direction of the surface area? What is the angle between f bar and a bar? What is the angle here? Now here in this case, theta is equal to what? Theta is equal to 90 degrees. Now tell me, what is the flux through this surface area a bar here? What is the flux through this surface area a bar? Tell me in this case. Tell me here, is the flux through the surface area, what you will get in this case? Let us say this is case 2. Let us say it is case 2. Tell me here. Tell me. What is the flux through the surface in this case, in case 2? Yes? I am waiting for your reply. Tell me, tell me. When theta equal to 90 degrees, what is the flux through the surface? Now here in this case, the flux through surface is equal to what? Flux through the surface is equal to what? Is equal to 0 or not? Yes or no? So no field is penetrating through the surface. Yes or no? So the field is parallel to what? Parallel to the plane of the surface. Yes or no? So that's why here there will be no field that is penetrating through the surface. So in this case, flux is equal to 0, right? So this is case 2 here. This is case 2. Next, case 3. Let us take case 3 here. Let us take case 3. Okay. Case 3. Right. Now here let us consider this surface area. Now let us consider the surface area like this. Let us consider the surface area like this, right? Okay. Now here let us assume here the vector field here is pointing like this here. Let us assume the vector field here is pointing like this. Okay, let us assume the vector field, this is f bar here, this is f bar. So f bar is pointing like this, and this is the surface area is present like this, right? So the direction of the surface is given by the unit normal drawn to the surface. Now in this case, this f bar is neither, this vector field is neither parallel to what? Parallel to the surface nor perpendicular to the surface. Yes or no here? So this f bar is neither parallel to the surface nor perpendicular to the surface. Now in this case, what we can do here? In this case, what we can do? Tell me. So we can resolve this f bar here. This f bar is neither parallel to the surface nor perpendicular to the surface. So you can resolve this f bar into two components. Yes or no? You can resolve this vector field into two components. One is what? One is parallel to what? Parallel to the surface, and another one is what? Another one is perpendicular to the surface. Yes or no here? So you can resolve this f bar into two components. One is parallel to the surface and another one is what? Perpendicular or normal to the surface. Now which component of the field is going to contribute for flux here? Now this vector field is neither parallel to surface nor perpendicular to surface. So you can resolve this vector field into two components. One is parallel to the surface and perpendicular to the surface. Now which component of this vector field is going to contribute for flux? See, the component that is parallel to the surface is not going to contribute for any flux. Yes or no? Only the component that is perpendicular to the surface. Yes or no? Only the component that is perpendicular to the surface is going to contribute for flux. Okay, so that means in this case, the flux value is going to lie between what here? Is going to lie between 0 and maximum flux. It is going to lie between 0 and maximum flux. So the flux through this surface is going to lie between what? Is going to lie between the minimum value and maximum value. So only a part of the vector field that is perpendicular, only the component of vector field that is perpendicular to the surface is going to contribute for what? Is going to contribute for flux. Yes or no here? Yes? Yes, Parameshwar, sir, I think comments are not uploaded fastly. Okay. Okay. Okay, Parameshwar, we will check that. Okay. Yes, sir, I am also feeling the same. I am getting the reply slowly. So that's what I am also feeling. Okay. Anyway, we will rectify that. See. So what is the conclusion we can make here is only the component of vector field, only the component of vector field that is perpendicular to the surface is going to contribute for flux. Or I can say only the component of vector field, only the component of vector field along the direction of the surface, is going to contribute for flux. And the component of the vector field that is parallel to the surface is not going to contribute for any flux. Right? Okay. So I hope it is understood here. I hope it is understood. Right? Right? Okay. Okay. So now see here. So I am giving that point here. I am giving that point here. This is very, very important here. This small observations will make you understand the concepts clearly here. Okay. So this is small observations are very, very important here. So what we have observed here? What we have observed? So only the component of the field, only the component of the vector field, only the component of the vector field that is along the direction of the surface, that is along the direction of the surface, or I can say or vector field that is along the direction of the surface, or I can say are perpendicular to the plane of the surface, or perpendicular to the plane of the surface. Okay. So is going to contribute, is going to contribute for the flux here, is going to contribute for the flux. Right? So I hope this point is clear here. I hope this point is crystal clear. Right? Okay. So only the component of vector field, only the component of vector field that is along the direction of the surface, or perpendicular to the plane of the surface. Both mean same or not? Yes or no? Along the direction of the surface or perpendicular to the plane of the surface. Both mean same here. Both mean same. So is going to contribute for the flux, So the component which is parallel to the plane of the surface is not going to contribute for any flux here, right? So we can so I will give one example here. So with that it is going to be very much crystal clear. Okay. So now let us take one problem here. So note it down here. So once it is completed, then we will take one problem here. So note it down here. So this is very, very important. Right? Okay. So please prepare a notes here for each and every lecture. Try to prepare a notes. So that is going to be very much helpful for you here. Okay. So now see here. Now let us consider a vector field. Vector field F bar is equal to vector field F bar is equal to x cube y ax cap minus x y square z ay cap. Okay, so you can write plus xy square z ay cap plus y z square you can add xy z square az cap. Right? So this is the vector field I have given here. Vector field F bar is equal to x cube y ax cap plus xy square z ay cap plus xyz square az cap. See, whenever they give the problem here, whenever they have given the problem, just identify x component, y component and z component here. So always write in this manner. So this is nothing but x component of the vector field, and this is nothing but y component of the vector field, and this is nothing but z component of the vector field. So always write in this manner. Okay. So they have given this vector field here. So then determine the flux determine the flux through the surface, or you can say determine the flux through x is equal to 3 plane. Determine the flux through x is equal to 3 plane defined by y is ranging from 1 to 5 and z is ranging from 2 to 4. So what they have given here, question is, see here. So vector field, they have given the vector field, some vector field they have given here. Now they are asking determine the flux through x is equal to 3 plane. That means they have given x is equal to constant plane here, right? So x is equal to 3 plane means x is equal to some constant plane, and in that plane x equal to constant plane means it will represent what, an infinite plane or not? Yes or no? It represents an infinite plane. So in that infinite plane they have given some region or some surface area. So that is defined by what? That is defined by y is varying from 1 to 5 and z is varying from 2 to 4. See, x is equal to constant plane means on that plane x value is going to be constant. Only y and z are going to vary. So in general y can vary from minus infinity to plus infinity and z can vary from minus infinity to plus infinity. So if you consider minus infinity to plus infinity, then it represents an infinite plane, right? So they have given the range for y, and z. Understood? So you have to consider this region in x equal to 3 plane. You have to consider only this region in x equal to constant plane, and you have to determine the flux through this region here, that means the field that is penetrating through this region. That's what you have to determine here. Yes. What here? Wait. Anand, sir, could you please confirm on my doubt as Parameshwar said? What is your doubt here? What is your doubt? Can you be specific about your doubt here? I will explain that. Okay, so repost your doubt here. I will explain that. See here. So this is the question. They have asked here. See. So they have given a vector field. They have given the vector field. So this is the vector field they have given, right? So this is the vector field they have given, and they are asking to determine the flux through x is equal to 3 plane defined by these parameters, defined by y and z. Okay. So now see here. Now if I consider this as y axis and this as z axis. Let us consider this as y axis and z axis, and this is nothing but what? This is nothing but, let us say, x axis. Okay. So now here this is nothing but, here this is 0 here, this is 0. Now if I consider a plane here, this plane is nothing but what? This is y axis, z axis is coming out of the board. So this will represent YZ plane. So at this YZ plane is located at what? Is located at x is equal to 0 location. This YZ plane is located at x is equal to 0 location. So now if you shift this YZ plane, to a location x is equal to 3, if you shift this YZ plane at x equal to 0 to x is equal to 3, then on this plane at each and every location x value is going to be what? X value is constant, that is x value is going to be 3. Only y and z values are going to vary. So now here I am drawing x is equal to 3 plane here, So let us consider this is x is equal to 3 plane, right? So let us consider this is x is equal to 3 plane, x is equal to 3 plane, right? So now what is the direction of this x is equal to 3 plane here? It is parallel to yz plane, it is parallel to yz plane. So if you draw the normal to this plane here, if you draw the normal to this plane, it is going to point in which direction? It is going to point in x direction. That means its direction is going to be along x, that is along ax cap direction. Right. Now here in this plane they have told that you have to consider the region, in this plane such that y must vary from where to where here? Y must vary from 1 to 5 and z is varying from 2 to 4, right? So this is the plane here, this is the plane. So in that in that you have to consider some region, you have to consider only a part of the region. So this represents what? This represents y, this represents y, yes or no? Okay. So this represents from here to here, represents range of y here, from here to here represents range of y. So this y is ranging from where to where? From 1 to 5, from 1 to 5. Right, and this represents, here it is coming out of the board here, this is z axis here, this is parallel to z axis, right? So z is varying from where to where? 2 to 5. So this is nothing but from here to here, represents what? Represents range of what? Range of z. So here this is the plane here, this is the plane you are having. Okay, in this x equal to 3 plane, so they have defined only this region here, that is y is varying from 1 to 5 and z is varying from 2 to 5. So it is like this, so y is varying from 1 to 5 and z is ranging from 2 to 4, right? So z is varying from 2 to 4 and y is varying from 1 to 5. So it is going to form this plane here, you are having this plane, right? Okay, now they have given some vector field and they are asking to determine what is the flux through the given surface. Right, okay. So how to determine this one here? See, we know that the flux through any surface here, so I am writing the solution here, see. So flux through any surface here, how we can represent here? We know mathematically how to represent flux through any surface. So we can represent it as double integral f bar dot what? F bar dot dA bar. Right. Now here this f bar is going to have which components here? It is going to have x component, right, y component and z component. So this f bar is going to have 3 components, that is x component, y component and z component. So this dA bar represents what here? This dA bar represents a small differential area on this surface, Now if you consider this surface, what are variables on this surface here? X is constant, yes or no? X is constant on this surface. So what are varying? Only y and z values are varying. So that means y and z are variables, yes or no? Y and z are variables. So that means what this differential area y and z are variables means, you have to multiply what? You have to multiply differential length along y into differential length along z, yes or no? dA bar is nothing but, the variables are nothing but dy and dz. And what is its direction? Its direction is along what? The direction of any surface will be perpendicular to that surface or not? Yes or no? So dy dz and its direction is along ax cap direction. So dy dz ax cap. Right. So in this manner you have to write the differential area. So if you know what are variables on that surface, then you can easily represent this differential area here. Yes or no? So here y and z are variables, so you have to write here dy dz and its direction is given by the unit normal drawn to that surface, that is along which direction here? ax cap direction. Okay. So now here we can easily solve the problem here. Now see here. Now here the variables are nothing but y and z. So you have to integrate with respect to what? You have to integrate with respect to y and z. You have to integrate here with respect to y and z. Okay, so one more point here, I have told that only the component of the field, only the component of the vector field that is pointing along the direction of the surface, only the component of vector field that is pointing along the direction of the surface is going to contribute for what? Is going to contribute for flux. Yes or no here? So only the component of the vector field that is along the direction of the surface is going to contribute for flux. Now here you are having x component, y component and z component. This y and z components, are parallel to what? Are parallel to the surface or not? Yes or no here? Y component is going to point along y direction, z component is going to point along z direction, right? So y component and z component are parallel to the surface. Okay, and x component here, x component of vector field is going to point along x direction. So this is the component, of vector field that is pointing along the direction of the surface. So y component and z component is not going to contribute for any flux, only x component of the vector field is going to contribute for flux. Yes or no here? Yes or no? Okay, so now you can directly write, there is no need to write the total expression and all. So now you can directly write integration from y, variables are y and z. So y is varying from where to where? Y is varying from 1 to 5 and z is varying from 2 to 4. Yes or no? Z is varying from 2 to 4. Wait. Z is varying from 2 to 4. And this vector field, you have to consider only x component of vector field here, x component of vector field. So what is the x component of vector field? That is x cube y ax cap, x cube y ax cap. So write down here x cube y ax cap, right? So dot dy dz ax cap, right? If you consider y component, you are going to have ay cap dot ax cap will become 0. If you consider z component is going to point along az cap direction. If you do the dot product between az cap and ax cap, that term will also go to 0. So only the left out term is only x component here, only x component, right? Okay. Okay. So identify the component that is along the direction of the surface. So only that component is going to contribute for flux, right? So now do it here. Now it becomes a simple integration here. Now see here, y is equal to 1 to 5. Now here x cube y ax cap dot dy dz ax cap, what you are going to get? You are going to get simply x cube y into dy dz, x cube y into dy dz, right? Now here x is constant with respect to this integration variables or not? X is constant with respect to this integration variables. You are integrating with respect to y and z. So x is constant with respect to this integration variables. So take x outside here. So you will get x cube here. So integral y equal to 1 to 5 and integral z is equal to 2 to 4. So what is left out here? Y into dy into dz. So now do this integration here. What you are going to get? You are going to get x cube into integration of y is nothing but y square by 2. Its range is from 1 to 5. Integration of dz is z and its range is from 2 to 4. So what you are going to get here? On this plane, x value is what here? X value is equal to 3. So wherever you will go on this plane here, x value is going to be 3. It is constant, right? Now here we know x value also. X value is equal to what? X value is equal to 3. So substitute 3 here. So you will get 3 cube, right? Next here you will get 1 by 2 into 5 square minus 1 square. 5 square minus 1 square. Here you will get 4 minus 2. 4 minus 2. So what you will get here? 3 cube, that is 27 by 2 into 25 minus 1, that is 24. 4 minus 2 is 2. So 2 will get cancelled. You will get 27 into 24. Okay, some units. So they have not mentioned any units here. So simply represent some units must be present here. So 27 into 24. So this is the value of the flux. That is penetrating through the given surface. Okay. So is it clear here? Yes or no? Tell me here, is it clear? right? Tell me here, is this problem clear? So Anand, what you are asking here? Sir, if a surface has some thickness, will the field lines penetrate for 90-degree angle? No, here whenever the angle between F bar and A bar, if the angle between F bar and A bar is 90 degrees, then the field that is penetrating through that surface will be always equal to 0. See, whenever that area is having some thickness means you don't say it as area, you have to consider the volume or not. We are not talking about volume here, we are talking about only surface area, right? So whenever the angle between the surface area and vector field is 90 degrees, then there will be no flux here, there will be no flux through the surface. Only the component that is along the direction of the surface is going to contribute for flux. Okay, so I hope it is clear from this problem also, right? Okay. Okay, yeah. So this is one example here, this is one example of flux, right? Okay, so I hope the concept of flux is clear here, I hope it is crystal clear. So next we will move on to the concept divergence. So next we will move on to the concept divergence here. So we will see divergence. Divergence, right? Okay. Okay, so now what I said here, divergence. So what is the definition of divergence? Tell me, what is the definition I said? So it is a measure of what here? Divergence. It is a measure of, how much of the given vector field, how much of the given vector field, how much of the, or you can say simply, how much of the vector field is leaving away, how much of the vector field is, you can say, spreading away, how much of the vector field is spreading away or leaving away or diverging away from a given point, See, I said already this gradient, divergence and curl all are defined at what? All are defined at a point, right? So see here, so what I am saying here, so here it is a measure of what? Divergence. It is a measure of how much of the given vector field, how much of the given vector field is spreading away or leaving away or diverging away from a given point, right? Okay, so what it is saying here, what do you mean by this statement here? So divergence means whenever you are calculating the divergence, what you are calculating means, you are calculating that how much of the, or you are measuring that how much of the given vector field, is spreading away or leaving away or diverging away from a given point, So how much of the vector field is spreading away from the given point or leaving away from the given point or diverging away from the given point. So that's what you are measuring here. Whenever you are calculating divergence, you are measuring how much of the given vector field is leaving away or spreading away or diverging away from the given point. Okay, so I will explain this with an example, right? Okay. Okay. So I will explain this with an example. So wait here, Parameshwar, what you are asking here? Angle is 90, sir. What is that? Angle is 90. Which one you are asking here? Angle is 90, sir. Okay. What you are asking? Sir, the angle between the plane of the surface and F is 90 degrees. Then no, the angle between the direction of the surface, the angle between the direction of the surface and the vector field, if it becomes 90 degrees, then it will be what? It will be 0, right? See, simply see this one here. So this is the surface here, this is the surface. So you are having some vector field here. If you are having some vector field, if you are having some vector field here, so what I said here, what I said, so this is the surface area, this is the surface area, or you can consider like this, the vector field you can consider in this manner also. So I said now, so only the field component that is perpendicular to the plane of the surface is going to contribute for flux here. Remember this, understood? Okay, perpendicular to the, only the component that is perpendicular to the plane of the surface, or you can say only the component that is along the direction of the surface. Okay. Okay, don't measure the angle with respect to plane and all here, take the angle between F bar and the direction of the surface here, that's it. Draw the normal to the surface, so it is going to give you the direction of the surface, and take the angle between this A bar and F bar. Okay. Okay. Right. Right. Is it clear here? Is it clear? Yes, here, whatever you are saying, whatever I am saying and whatever you are saying, both are same here. The angle between plane of the surface and F bar is 90 degrees, flux becomes maximum. Yes. So don't confuse like that here, don't confuse yourself like that. Okay. So just follow one method, it is going to be always better. Otherwise you will get confused. Don't measure the angle with respect to the plane. Measure the angle between the vector field and the direction of the surface. Right. Okay. So I hope it is clear here. I hope it is clear. Okay. Yes. Okay, so coming to divergence. So it is a measure of how much of the given vector field is spreading away or leaving away or diverging away from a given point. So whenever you are calculating the divergence of a vector field, what you are calculating is how much of the given vector field is spreading away or leaving away or diverging away from the given point. So this is what you are measuring whenever you are calculating the divergence. Okay, so I will explain this by taking some examples here, So now let us consider I have taken a positive charge here. Right. So now from here we know that always the field lines are going to emanate from a positive charge. Always they are going to point away from positive charge. Yes or no? So whenever I place a positive charge, we know that the field lines are going to be radially outward. Yes or no? So the field lines will be like this. So the field lines will be radially outward here. They will be radially outward. The field lines are radially outward. Right. We know that whenever you place a positive charge, we know that from the positive charge the field lines will emanate radially outward, okay, this thing we know. Now see here, now see here so now if you consider the divergence exactly at this point here, or if you try to measure how much of the vector field that is leaving exactly at this point, so that means exactly at the location of source here, exactly at the location of this charge, yes or no? See, for these field lines, this Q, this positive charge is acting as what? Is acting as a source or not? For these field lines, this charge is acting as a source, yes or no? So all the field lines are radially outward from this charge. All the field lines are moving away, or all the field lines are spreading away, or all the field lines are diverging away from this source, or from this charge. Yes or no? So that's why if you try to determine the divergence, exactly at the location of the source, what you are going to get? You are going to get not equal to 0 or not? Divergence will be not equal to 0. Why? Means from this point you are observing that all the field lines are leaving from this point. Yes or no? So how much of the field is leaving from this point is nothing but what? Is nothing but divergence at that point. That means if you try to calculate the divergence at the location of the source here, so this is nothing but source, right? So this is nothing but source. So at the location of the source, if you try to determine the divergence, you are going to get what? You are going to get not equal to 0. Yes or no? Because all the field lines are leaving from this point. Right. So in this case you are going to get divergence not equal to 0. Now here you are measuring how much of the vector field is leaving away from the given point. Now here all the field lines are leaving away from the given point, and hence you are going to get divergence will be greater than what? Will be greater than 0. It is not equal to 0 and it is going to be what? It is going to be greater than 0. Yes or no? Okay. Now if I consider negative charge here, let us assume I am considering a negative charge. Now in this case what will happen here? See, so now in this case all the field lines are going to converge. Yes or no? All the field lines are going to converge radially towards what? Towards the negative charge. All the field lines will move radially towards what? Towards the negative charge in this manner, right? So all the field lines are converging towards this point, right? Okay. So now see here, now in this case also, all the field lines are converging towards this point. Yes or no? So now here, if you try to measure how much of the field that is leaving from this point here, what you are going to get? Here no field is leaving from this point, but all the field lines are converging towards this point. Yes or no? So convergence means what here? Convergence is opposite to what? Is opposite to divergence. Yes or no here? So instead of the field lines that are leaving from this point, what is happening here? All the field lines are converging towards this point. So converging towards this point, convergence is nothing but what? Convergence is nothing but negative of what? Negative of divergence. I can say all the field lines are sinking towards this point. So I can say here what is present here? Sink is present. I can say sink is present. Now here the field lines are not leaving from this point, instead the field lines are converging towards this point. That is nothing but negative of what? Negative of divergence. Yes or no? So now in this case exactly at the location of sink, exactly at the location of minus q, or exactly at the location of sink, the divergence will be what? The divergence will be not equal to 0, and this divergence is less than 0. Yes or no here? Okay. So is it clear here? Yes or no? Okay. Now see here, one more point we can observe here is, see, now if I try to determine the divergence at this point here, so at this point what is happening, whatever the field that is entering towards this point, the same field is leaving from this point or not? Yes or no? So whatever the field that is entering towards this point, the same field is leaving from this point or not? So that means, what is the net field that is leaving from this point here? What is the net field that is leaving from this point? Is equal to 0 or not? So that means at this location, what you are going to get? Divergence is equal to 0. I said divergence is defined at a point, right? Now similarly, if you consider at this point here, now here also, whatever the field that is entering towards this point, the same field is leaving from this point. Yes or no? So that means here also, at this location also, what is the net field that is leaving from this point here? Is equal to 0. That means here divergence is equal to what? Divergence is equal to 0. Now here similarly, if you consider some point here, so here also the same thing here, whatever the field that is entering, the same field is leaving. So at this location also, divergence is equal to 0. So that means except at the location of source here, you can consider any other point. At all the other points, we are getting divergence is equal to what here? Divergence is equal to 0. Except at the location of what? Except at the location of source. Right. Now similarly, coming to this one, here also, if you want to determine the divergence at this point here, so at this point, whatever the field that is entering, the same field is leaving. So divergence at this location will be equal to what? Will be equal to 0. So whatever the field that is entering, the same field is leaving, and hence divergence at this location is also equal to 0. So now you can consider any other point here. You can consider any other point other than what? Other than this minus q, point. Okay, other than this sink point, you can consider any other point. In this region. So everywhere, what you are going to get, whatever the field that is entering, must be equal to what? Will be equal to the field that is leaving from the point. Okay, and hence at each and every point in the region, what you are going to get here? Divergence is equal to what? Is equal to 0. Divergence is not equal to 0 only at the location of what? Only at the location of sink. Since all the field lines are converging towards this point, it is opposite to what? Convergence is opposite to the divergence. Yes or no? And hence the divergence will become what here? Negative. And it is not equal to 0 exactly at the location of what? Exactly at the location of sink. Right? Yes or no here? So is this point clear here? Neeli Sai Kumar, divergence is like a water fountain, water coming out from fountain is a field. Okay, or you can take many examples for divergence, right? Okay. So is it clear here up till now? Now if I consider at this location, if I consider plus q and minus q, I have considered plus q and minus q. So both the charges are present at the same location, plus q and minus q. So if I consider plus q and minus q, so what is the net charge here? In this case, the net charge at this location, is equal to 0. So that means if it just act like no charge here, no charge region. Yes or no? Plus q and minus q will give you what? Net charge will be equal to 0, right? So I am assuming both charges plus q and minus q are located at the same point, I am assuming, right? So then in that case, the net charge at this point will become equal to 0. So if the net charge at this point becomes 0, then in the vicinity of this, there will be no field here, right? So there will be no diverging field or there will be no converging field. In this case, what happens here at this location? Exactly what you are going to get? Divergence is equal to 0. You don't observe any field that is leaving from this point, or you don't observe any field that is converging towards this point, and hence divergence at this location will be equal to what? Will be equal to 0. Right. So from these three, what you can observe here? Tell me. Is these points clear here up till now? Give some comments here, give some comments, so that we have to interact with each other, whether are you able to understand or not. Yes or no? Yes, is it clear up till now? If it is clear, we will move on here. If it is clear, we will move on. Yes? Okay. So I hope it is crystal clear here. I hope it is crystal clear. Right? Okay. So from this here, from these three cases, let us say this is case 1 and this is case 2 and this is case 3. So from these three cases, what you have observed here, what you have observed? So whenever you are calculating the divergence exactly at the location of the source, you are getting divergence not equal to 0 and divergence greater than 0. Right? And whenever you are calculating the divergence exactly at the location of sink, here also you got divergence not equal to 0 but divergence less than 0. Now if you consider at a location where neither source is existing nor sink is existing, yes or no? I can say here neither source is existing nor sink is existing because one is nullifying the other. Yes or no? So in this case, I have seen that divergence is equal to 0. And also if you consider these points here, at these points you are not observing any sources at these locations. Yes or no? So at these locations also, what we got here, divergence is equal to 0. Understood? So at these locations also we got divergence is equal to 0. So at these locations there will be no source, there is no source. Right? And here at these locations there is no sink at all. Right? So at these locations also we got divergence is equal to 0. And here since there is no net charge, here also we got divergence is equal to 0. So where we are getting divergence not equal to 0 here? Only at the location of source and only at the location of what? Sink. Yes or no? So that means what is the conclusion we can make here? For the divergence to exist, there must be what? There must be either sink or source must be present at that point. There must be either source or sink must be present at that point. If neither source nor sink exists at that point, then in that case divergence will be equal to 0. So this is the conclusion we can make here. This is the conclusion we can make. So what is the conclusion here? What is the conclusion? So for the conclusion, so for the divergence to exist, for the divergence to exist, for the divergence to exist at any point, then there must be either source or sink must present at that location or at that point. So this is the conclusion we can make here. So this is also important conclusion here. This is also important conclusion. See, if you understand this flux and divergence clearly, then you can easily understand Gauss law here. Then you can easily understand Gauss law for electric field and Gauss law for magnetic field. Right? Next, if you understand circulation and curl, you can easily understand Ampere's law and Faraday's law. So with that, 4 Maxwell's equations will be completed. Yes or no? Gauss law for electric field, Gauss law for magnetic field, and Ampere's law and Faraday's law. So with this 4, you are going to get all the 4 Maxwell's equations. So for all these 4 Maxwell's equations, this is the foundation here. This is basic. You have to understand. Right? Okay. So if you understand this flux and divergence clearly, then you can easily understand Gauss law. Right? So what I am saying here, for the divergence to exist at any point, then there must be what? There must be either source or sink must be present at that point. There must be either source or sink must be present at that point. So if neither source nor sink is present at that point, then the divergence at that point will be equal to what? Will be equal to 0. Will be equal to 0. Right? Okay. So this is very, very important here. This is very, very important point. Right? Okay. Okay. So I hope it is crystal clear. So Parameshwar, sir, comments are not update fastly, sir. We are responding. Okay, yaar, okay. I will check that here. I will check that later once this session is completed. I will check that, and I will rectify that issue from tomorrow onwards. Okay. Okay, yaar. Okay. So I hope it is clear here. I hope it is crystal clear. Now I can take some more examples for divergence here. See here. Now let us consider some field is entering. Let us assume this is the vector field here. This is some vector field, right? So this vector field is entering towards this point here. This vector field is entering towards this point. Let us assume the vector field is entering towards this point. Next, the field is leaving from this point. So the field that is leaving from this point, I am representing like this. Okay, so this is the field that is entering. This is the field that is entering towards this point. This is the field that is entering towards this point, and this is the field. This is the field that is leaving from this point. So this is the field that is entering towards this point, and this is the field that is leaving from this point. Okay, so this is nothing but entering field. This is the field that is entering, and this is the vector field that is leaving. This is the vector field that is leaving. So now tell me, see, whenever you are calculating divergence, what you are calculating here? You are determining how much of the net field that is leaving from a given point. How much of the net field that is leaving from a given point? Yes or no? Or how much of the field is diverging from a point? That's what you are determining. Now if you observe here at this point here, at this point, what is happening here? So this is the field that is entering towards this point, and this is the field that is leaving from this point. Now tell me whether this leaving field is greater than entering field, or it is less than entering field, or it is equal to entering field. The field that is leaving from this point here, is greater when compared to what? The field that is entering towards this point, or not? Yes or no here? Yes or no? So whatever the field that is entering towards this point is lesser when compared to the field that is leaving from this point, right? So that means the converging field is lesser when compared to the diverging field, or I can say the entering field is lesser when compared to leaving field. So now what is the net field that is leaving here? What is the net field that is leaving? So net field that is leaving from this point, net field that is leaving from the given point, I can represent it as what here? So this is nothing but what? Leaving field minus what? Minus entering field. Leaving field minus entering field. Now here leaving field is greater than what here? Entering field. So you are going to get this value as greater than 0. So the net field that is leaving from this point is greater than 0. That means you will get divergence is greater than 0 at this point. So if divergence is greater than 0, that means at this point what must be present here? Source must be present. Yes or no here? So there exists some source of this vector field at this location. So that's why whatever the field that is entering is lesser when compared to the field that is leaving, right? So that means exactly at this point some source must be present. Understood here? Is this point clear? Okay. Now similarly in the same manner, if I consider the vector field, like this. So let us say this is vector field. Let us say this is entering field here. This is entering, right? So here I am considering a point. Now here the field is leaving. Here. The field is leaving from this point here, Now if you observe, this is the field that is entering towards this point, and this is the field that is leaving from this point. So that means this is field that is leaving. Now if you observe, the field that is entering towards this point is greater than what? Is greater than the field that is leaving from this point or not? Yes or no? So that means in this case, the entering field is greater than what? Is greater than the leaving field, is greater than the leaving field. Yes or no? So that means the converging field is greater when compared to the diverging field. So in that case, what is the net divergence you are going to get? Net divergence is going to be negative, or the net field that is leaving from this point will be what? Will be negative. So the net field that is leaving from this point is nothing but what? Leaving minus what? Leaving field minus entering field. Leaving field minus entering field will be less than what? Will be less than 0. So this is the net field here. This is the net field leaving from the given point. Net field leaving from the given point. Right. So from the given point, that is leaving minus entering. So you will get this value as what? Less than 0. This implies divergence is less than 0. So if divergence is less than 0 means divergence is negative. Divergence is negative. Yes or no? Okay. So if divergence is negative means what is present at this location here? At this location, what is present? There must be a sink. There must be a sink. Right? There must be a sink. Okay, now I can take one more example like, so I hope you have understood these two examples here. Okay, so next one is, let us say this is the field that is entering towards this point. This is the field that is leaving from this point. So this is entering and this is leaving. Now in this case you can observe that whatever the field that is entering, the same field is what here? The same field is leaving from this point, right? Okay. So here in this case, net field leaving from the point, net field leaving from the given point, is equal to what? Is equal to leaving field minus what? Minus entering field. So leaving is same as what? Entering. So you will get what? You will get 0. That means in this case you are going to get divergence is equal to what here? Divergence is equal to 0. Divergence is equal to 0. Right? Okay. So that means at this location, neither source, neither source nor sink will exist at this location. Neither source nor sink will exist at this point here. So whatever the field that is entering, the same field is leaving, and hence in this case the divergence at this location will be equal to 0. That means neither source nor sink will exist at this point. Yes or no here? Okay. So I hope these examples are crystal clear here. Crystal clear. So we have seen when you are going to get divergence less than 0, and when you are going to get divergence greater than 0, and when you are going to get divergence equal to 0. So what is the meaning of divergence greater than 0? So that means at that point, if source is existing here, if source is existing at a point, then you are going to get divergence greater than 0. If sink is existing at that point, then you are going to get divergence less than 0. If suppose neither source nor sink is existing at that point, then in that case you are going to get divergence is equal to 0. Yes or no here? Yes or no? Okay. So I hope it is crystal clear here. I hope it is crystal clear. So let me know, is it crystal clear here? Yes or no? Neeli Sai Kumar, how to identify the entering field is large or small? I have given in the diagram na. See here. See this vector field, whenever I am representing this vector field, the length of these vectors is greater. Yes or no? The length of these vectors is greater when compared to the length of these vectors. Yes or no? So that means here the entering field is greater, is having greater value when compared to what? Leaving field. Right? Okay. So if you observe here, the length of the vector field, the length of these vectors are smaller when compared to the length of these vectors. So in this manner, I have differentiated between entering field and leaving field. Now here, since I have represented the leaving field with what? With larger length of the vectors, so it represents leaving field is greater when compared to what? When compared to entering field. So in this manner, I have explained here. Clear? Yes or no? Yes, yes. Okay, I hope it is clear here. Yes, very good. Okay, fine. Okay. Okay. So you have understood what do you mean by flux, what do you mean by divergence, yes or no? Their physical interpretations also you have understood clearly, right? So now see, in exams they may ask you a questions like this. Directly they may ask you the questions in this manner here. So what is the divergence of the vector field? What is the divergence of the vector field exactly at the location of charge, that means whether it is equal to 0 or not equal to 0, or it is greater than 0, less than 0, like that they may ask you the questions. Or they may give some point here, and ask you what is the divergence exactly at this point other than the location of charge. Okay, so then you must answer divergence is equal to 0 if the point is other than the location of source. Okay, so in that manner they can frame the questions here, some theoretical questions or conceptual questions, right? Okay, yeah. So this is all about divergence. So this is the physical interpretation of divergence here, right? So in the previous session itself, I have represented mathematical expression for divergence. Yes or no? Mathematical expression for divergence. So what I have said here, so in the previous session itself, I have explained this one here, divergence of vector field. How to expand this one? So this is equal to what you are going to get, dou fx by dou x plus what? Dou fy by dou y plus dou fz by dou z. So this is what here? This is a scalar quantity. So how to determine divergence of a given vector field? What you have to do? So whenever they have given the vector field here, so take x component of that vector field. And differentiate that with respect to x. Plus take the y component of the vector field. And differentiate it with respect to y. And take the z component of vector field and differentiate with respect to z. That is going to give you what? That is going to give you divergence. And also one thing I said that if x component is a function of y and z. If x component is a function of y and z, and if y component is a function of x and z, and if z component is a function of x and y. So if the vector field looks like this here, then you can simply say divergence of f bar is equal to what here? Divergence of f bar is equal to 0. Why here? Whenever you are calculating divergence, what you are doing? You are taking x component and differentiating with respect to x. If x component is a function of only y and z, it is independent of x, then you are going to get here what? 0. If you differentiate this with respect to x, you are going to get 0. And if you differentiate this y component with respect to y, so here y component is a function of x and z, it is independent of y. So this term will also go to 0. So here z component is a function of x and y, and here you are differentiating with respect to z. So this component will also go to 0. In that case, divergence of f bar is equal to what? 0. So if you see a vector field in this manner, then blindly say divergence of that vector field is equal to what? Is equal to 0. I am not saying only this type of fields are going to produce divergence of f is equal to 0. There are many other fields, but for this type of field, vector field, you can directly identify that divergence of this type of vector field is always equal to what? Is always equal to 0. Right? Okay. Yeah. Okay. So now see here. So if the divergence of vector field is equal to 0 here, if the divergence of any vector field is equal to 0, then that vector field is said to be, divergence-less or solenoidal. Then that vector field is said to be what here? Divergence-less or solenoidal. Okay, so write down that point here, write down that point. So if okay, so if divergence of f bar is equal to 0, if divergence of f bar is equal to 0, that means divergence of any vector field is equal to 0, then f bar is said to be what here? F bar is said to be divergence-less, is said to be what? Is said to be divergence-less or solenoidal, right? So if divergence of any vector field is equal to 0, then that vector field is said to be what? Is said to be solenoidal, right? Okay, yeah. Okay, so now I will give one example here, based on this. So let us take f bar, is equal to x square y ax cap plus 4 into k minus 1 into y ay cap plus z square y az cap, So if the vector field, if f bar is solenoidal, at a point, if f bar is solenoidal at a point 1, 2, 3, then determine the value of k, right? Then determine the value of k. Do it here, do it. Simple problem here, What I have given? I have given some vector field and I am saying that this f bar is what? Is solenoidal. At what point? At 1, 2, 3. At a point 1, 2, 3. So that means at that point this vector field is going to have divergence. Divergence of this vector field exactly at this point will be equal to what? Will be equal to 0. In that case, what is the value of what? What is the value of k? You have to determine the value of k, right? Okay, tell me the answer here, tell me the answer. I am waiting for your answers here. It is simple. What I said, don't write every time divergence of f bar is equal to, don't expand all these things. Okay, you can do directly, So divergence operation must be present in your mind itself. Okay, so you can do directly. So what you can do? So just first what I have told here, just write the x component of the vector field and y component of vector field and z component of vector field. So divergence means what? Take x component and differentiate with respect to x. So take x component and differentiate with respect to x. What you are going to get? 2xy plus take y component and differentiate with respect to y. What you are going to get? 4 into k minus 1. Take z component and differentiate with respect to z. What you are going to get? 2zy. So this is nothing but divergence of f bar. So they said that f bar is solenoidal. That means divergence of f bar must be equal to what? Must be equal to 0. Yes or no? So at what point? 1, 2, 3. So divergence of f bar is this value, right? Now in place of x, y and z, substitute 1, 2, 3. So then what you are going to get? Tell me what you are going to get. Substitute here x is equal to 1, y is equal to 2. Right, and here z is equal to 3 and y is equal to what? Y is equal to 2. Substitute those values. What you are going to get? So 2 into 2, 4 plus 4 into k minus 1 plus 2 into 3, 6 into 2, 12. This must be equal to what? This must be equal to 0. right? So 4 into k minus 1 is equal to minus 16, yes or no? Okay, so 4 ones, 4 fours, so therefore k is equal to what here? K is equal to minus 4 plus 1, that is k is equal to minus 3, k is equal to minus 3, yes or no? So don't write every time, don't expand this divergence operation and all. So just you have to calculate everything in your mind here. You know that, take x component and differentiate with respect to x, take y component and differentiate with respect to y, take z component and differentiate with respect to z, and substitute the values of x, y and z and equate it equal to 0. So in this manner you have to solve the problem very fastly here. Okay. So I hope it is clear here. I hope it is crystal clear. Yes, Parameshwar, Piyush. Yes, correct here. Minus 3, correct. Very good here. Very good. Very good here. Okay. So I hope you have understood clearly about divergence and flux. I hope you have understood clearly about divergence and flux. So now I am winding up the session here with this, but tomorrow I am going to explain divergence theorem here. Tomorrow I am going to explain divergence theorem. So you have understood this divergence, you have understood what do you mean by divergence mathematically, as well as you have understood its physical interpretation also, right? Okay, so tomorrow we are going to see what do you mean by divergence theorem, what is divergence theorem. So once we complete this divergence theorem, then we are going to study about curl here. We are going to study about curl. Okay, so in order to understand curl, you have to understand what do you mean by circulation of vector field. What do you mean by circulation of vector field around any closed loop? How to determine that? So once we understand about the circulation, then we'll go for curl here. So tomorrow we are going to study divergence theorem. Once we complete divergence theorem, then we'll go for what do you mean by circulation of vector field around any closed loop. Then once we complete this, then we'll go for what? We'll go for curl. Okay, so before divergence we have covered the concept of flux. So before curl we are going to cover the concept of circulation. Understood? Okay, so once we complete this, then we'll go for Stokes theorem here. So if you understand circulation and curl, then you can easily understand Stokes theorem. Now you have understood divergence and flux, and hence you can easily understand this divergence theorem. Okay, so we are going to cover these topics in the next sessions here, but tomorrow I am going to start with this divergence theorem. Okay, so attend every class here regularly, so that you can easily understand here. You can easily understand the subject if you attend the session regularly. Okay, so regularly if you attend the session, you are going to understand the subject very clearly here in a crystal clear manner. Okay, and it is very easy for you to score the marks in this subject if you understand the concepts clearly. Right? Okay, so I hope you have enjoyed this session. So in the same manner, tomorrow we are going to start our class exactly at 4 p.m. here. Okay, so with this I am winding up the session. So give some comments here. Have you enjoyed the session? Yes or no? Neeli Sai Kumar, thank you sir for such crystal clear explanation. Thank you here. Thank you. Okay, so everybody understood here? So give some comments in the comment section so that we can wind up the session. Yes. Parameshwar, thank you very much sir. Thank you. So please attend the session here regularly, and share it to your friends also. So that everybody will get benefited. Right? Okay here. Thank you very much. So I am winding up the session here. We will meet tomorrow exactly at the same time, 4 p.m. Okay here. So take care. Bye bye.